This question is about periodicity, the period for elements and their compounds. So this is probably a bit of an application question of the A1 pack, the AS pack on periodicity, and the A2 pack on period 3 elements, applying it to a new period in the periodic table. State the meaning of the term periodicity. Well, periodicity is about the repeating patterns in properties that we see across the periodic table. So they're wanting you to make sure that you put that word repeating, pattern or trend, and it can be in any kind of chemical or physical property. Then it wants the period for element with the highest electronegativity value. So you need to look at the periodic table and remember that electronegativity increases as you go from left to right and decreases as you go down. So we're kind of wanting the top right element in period 4. But remember that the noble gases don't have electronegativity values. So you want the element in group 7. So we're going along, we want the element in group 7 of period 4. So if you look at your periodic table, you'll find that that happens to be bromine. Period 4 is the row that starts with potassium. And that's because if you get caught out, remember that hydrogen and helium are period 1. So period 4 is the row that starts with potassium. So we're going along to the end of that row. We're finding the group 7 element. It's bromine. Then it wants us to identify the element in period 4 with the largest atomic radius. Now again, remember that atomic radius decreases as you go across the row. So actually we want the element at the beginning in group 1, which is potassium. And the reason for that is all the elements in group period 4 have the same number of shells. Have the same number of shells, so they all have the same number of electron shells and similar shielding. Not exactly the same shielding because every electron affects the shielding, but they have the same number of shells and similar shielding. But potassium has the fewest protons holding on to those shells. So size actually decreases across the row. Then we've got the equations for 2 reactions of arsenic 3 oxide. Name the property of arsenic 3 oxide that describes its ability to act in these 2 ways. And the key thing is, in the first equation, it's acting with an acid, and the second, it's reacting with a base. So in the first equation, because it's reacting with an acid, it is a base. But in the second equation, it is an acid. Something that can act as both an acid or a base is described as amphoteric. And then the last thing is says complete the equation. So we're just balancing this equation. It does look like it's going to be fairly complicated, and we can see that there are metals. We can see sort of straight away that there's a zinc metal reacting, and so this is a redox reaction. Often with a redox reaction, if you're struggling to balance them because they look complicated, what you might want to do is look at oxidation states. So we can see in here that arsenic, each oxygen is -2, so each arsenic is +3. And zinc here is 0. And at the other side, the arsenic has gone to -3 because each hydrogen is +1. And the zinc has gone to +2 because a nitrate ion is -1. And zinc's only other oxidation state other than 0 is +2 anyway. So we've got 2 arsenics, each going each going down, not going up, going down 6, but we've got 2 of them. So in total, we've got a sort of reduction in oxidation state of 12. Now the zincs only go up 2. We need to go up 12 in total for the electrons to match. So we're going to need to have quite a lot of these zincs. We're going to need to have 6 of these zincs, each going up 2 to make the increase in oxidation state match the decrease. So if we know that we have to put a 6 in front of the zincs, and we're going to need to put a 2 in front of this arsenic because there was 2 arsenics in the first compound. The rest of it should be fairly easy to balance once we know that. So we can now add up the oxygens or the hydrogens. I'm going to do the oxygens simply because they're only in one compound on the right. So on this side, I can see that in each zinc nitrate there are 6 oxygens, but I've got 6 zinc nitrates. So I've got 36 oxygens in total on this side, plus some here. And I've got then more oxygens over here and here. I know that because I've got 6 zinc nitrates, each one with 2 nitrate ions in, I could know that there's going to be 12 nitric acids. So that's probably where I would go next, because actually the oxygens are quite complicated. So I might just look at the nitrates as a whole. So 2 nitrate ions in every zinc nitrate, 6 zinc nitrates, so that's 12 nitrate ions, so 12 nitric acids. Now the hydrogens, 12 hydrogens, there's already 6 in this arsenic hydride, so there needs to be another 6, so 3 waters to balance that out. Now if I check the oxygens, we had 36 plus 3 is 39. We got 3 add 36, that's 39. So it's a very tricky equation to balance. In an exam, if you were really struggling with this would be something to come back to when you have time at the end.